Hello! In this video, I'm going to show you how to integrate trig functions using identities, trig identities. Now, most of the problems that we look at in this section deal with a sine and a cosine together with some exponents on them, or a tangent and a secant with some exponents on them. It might just be one of them, though. You don't have to have two trig functions in there to use these methods, so keep that in mind. If the exponents are all odd on any trig functions that show up, then we usually use a Pythagorean identity, particularly one of these two, depending on whether you have sines and cosines or tangent and secants in there. And you might have to solve them for one or the other trig function in order to do some kind of substitution. If the exponents are all even, you don't have any odd exponents, then the other option, which is a little more work, so it is the second choice here, is to use one of these double angle identities. And that just kind of depends on whether you have a sine or a cosine. So particularly this works for the top example there. Okay, so we're going to do an example of each of these where I have odd exponents and only even exponents to see how I can use these identities to solve the integral. In this first one, you can see I only have odd exponents. I've got a cubed and a first power. And when you have a choice here between which one you're going to deal with, you always want to choose the odd exponent over the even, because those would be more work to deal with an even exponent. And then if they're both odd, go with the larger one. That is the one that you're going to mess with and use your trig identity on. It just makes everything go much faster. There's less algebra needed when you start with the larger of the exponents. So for this one, I'm going to focus on that sine cubed of x, and I'm going to start out by splitting off one of the signs from it. So one sign comes off, which will leave me with an even exponent on the rest of the sine functions in here. So here it's sine squared. It's always just one that I kind of peel off from there. And so the part in parentheses, the sine squared, is the part that I'm going to swap out using our Pythagorean identity here. So sine squared of x is going to be equal to 1 minus cosine squared x when I solve the Pythagorean identity for sine squared. And so I'm going to swap out the piece in parentheses. So I now have a 1 minus cosine squared x in the parentheses. At this point, what I want to do is a u substitution. And I'm always going to choose u to be the trig function that is in the parentheses there that got swapped in to the integrand. And so I'm not going to take the exponent. It's just going to be u is equal to cosine of x. Taking the derivative of that, I get a negative sine x dx as my du. And so this is why that I wanted to kind of save that one sine of x, is now I can swap that out for the du, or with when I add in the du. So doing the u substitution, I get a negative out front from the du, and then the sine of x is gone and replaced with the du as well, and I have 1 minus u squared, replacing the piece in parentheses, and then that extra cosine that was hanging out after the parentheses is another u right here. At this point, I just have a polynomial. So I'm going to distribute everything out, get rid of those parentheses. So distributing the negative and the u into the binomial there in parentheses. And I end up with u cubed minus u when that is all distributed out. And from here, I can just integrate this using the power rule. So I end up with 1/4 u to the 4th minus 1/2 u squared plus my constant of integration. And the last step here is to reverse the u substitution, so I end up with an answer in terms of x. So I get a final answer there. So that's how you use the trig identities when you have an odd exponent in there. It doesn't matter if the other one's negative. I just need one odd exponent to make this work. The other example is when there are no odd exponents and you only have negative or even exponents to deal with. And in this case, because I have a sine to the 4th power of x, I'm going to be using the double angle identity for sine squared. First thing I'm going to do is I need to have a sine squared in there somewhere to swap out using this identity. So I rewrite this as sine squared squared. So it's still to the 4th, but now I have a sine squared x in the parentheses there, and I'll swap that out for the 1/2 times 1 minus cosine of 2x. All right, remember, I still have the squared on the outside, so I'm going to have to deal with that now. So the 1/2, I'm going to go ahead and square that, throw it out in front of the integral, and then I'm going to square the rest of that, remembering that I have to FOIL it all out. So I should end up with a trinomial here after I've distributed that square. A common trap here is to just square both terms, and then you miss that third term. Now, if you're following along with this is a good point to pause the video and kind of square that out, because I'm going to jump straight to what it simplifies to next. So this is what I ended up with from squaring that. And you can see that I still have a cosine squared. I have a trig function squared in here, which means I'm going to need to do another trig identity to bring down that exponent to something more manageable. So I'm going to bring in the other double angle identity for cosine squared x, and I'll swap it out for that third term. The other two I'm going to be able to integrate with not too much problems. A u substitution will take care of that cosine of 2x in the middle. So replacing that, and I went ahead and distributed the 1/4 in at this point. It just made it easier because I got so many terms floating around. So that's distributed in to each term, and then the cosine squared of 2x gets swapped out. And be careful, you're doubling whatever's inside the trig function. So I had a 2x, so I double that to 4x when I use this identity. So I got some more simplifying to do. I'm going to go ahead and do some distributing here to get rid of some of these parentheses. And I end up with this here. And you can see I've got a 1/4 and a 1/8 here, so I can go ahead and combine those. And I'm also going to split this up and integrate each term separately. Since they all have to be integrated a little bit differently, I'm going to go ahead and split this up into 3 separate terms. So I have a 3/8 from adding those two constants together, and then my cosine of 2x and my cosine of 4x. All with their own coefficients. The coefficients is where I always make mistakes here, so take your time and make sure you get those coefficients right. So I'm going to do a u substitution for the middle one, cosine of 2x, and another u substitution for the third one. I'll use a different letter, so I'm not using the same thing twice and confusing myself. So I'll use w for the third one, and w is 4x. Okay, so I do my substitutions. Right here, adding in, I'm going to have to add in a 1/2 to the middle one to account for this 2, and a 1/4 to the third one for that 4 there. And then I go ahead and integrate those, and then reverse the substitution, and I get my final answer. Okay, so these can get kind of long. The higher the exponent, the more work they're going to be. So take your time, give yourself some space, and be really careful with those fractions. Use your calculator for those. Okay, so there's our example of how to deal with an even exponent. I've got 2 more examples for you to try on your own in the guided practice. If you're in my face-to-face class, make sure to work those out and bring them to class for discussion. These have tangents and secants in there, so you're going to be using the other Pythagorean identity with those 2 trig functions in there here. So good luck, and I will see you later.